day. This is Robert Kleinberg speaking to you from Cambridge, Massachusetts. It's a pleasure to be speaking at this MIT A+B Applied Energy Symposium. The topic I'm speaking about today is Environmental Protection Agency methane emission controls. What needs to be fixed? Here is a very short outline for this relatively short talk. First, I'm going to tell you why methane is important as a greenhouse gas, and then why methane emissions are hard to control. The balance of the talk will be talking about regulatory solutions, good and bad. So just first to start out, let's just look at the big picture of greenhouse gas emissions from the United States. This is data from the Environmental Protection Agency and shows in this formulation that carbon dioxide is responsible for about 80% of the global climate change effect of greenhouse gases, as shown by the large blue slice. The next most important greenhouse gas is methane, responsible for about 10%, and then followed by nitrous oxide, a bit less, and then trace compounds. So looking at this chart, we would come to the conclusion that really carbon dioxide is really the only thing we really need to worry about. The other gases are of substantially less importance. But that is actually misleading. It's not true, as shown by this next slide. These are results computed by Drew Shindell of Duke University back about 10 years ago, but the results are still current. On the horizontal axis is a time scale from 2010 to 2070. The vertical axis is a global average temperature change with the baseline being the years 1890 to 1920, and the temperature scale is in degrees centigrade. Now, the red line is Shindell's reference case, which is basically business as usual, sort of doing what we're doing. And you can see that in that case, global average temperature rises steadily throughout the next 60 years and beyond. And this is not a desirable situation. The second case Shindell computed was one in which carbon dioxide reductions were implemented according to a plan prescribed by the International Energy Agency. That's shown in blue. The idea being that carbon dioxide reductions would start in the year 2012, which is the date of Shindell's paper, and then continue on indefinitely, and that's shown by the blue line. But you can see that for the first 30 years of CO2 reduction, there's actually no effect on the rate of temperature change. It sort of continues on following the reference case, and only after about 30 years does the temperature start to moderate. And the reason for this is simple. Basically, there's already a lot of carbon dioxide in the atmosphere, and carbon dioxide has a very long residence time in the atmosphere. So you can be cutting back on carbon dioxide for decades before you start seeing any effect. Now, once the effect takes hold, it's substantial, as shown by the blue. But if you want an immediate, short-term effect on climate change, and this summer has convinced us that we probably do want a short-term temperature modification, we have to look at methane, which is shown by the green line. Now, methane is a very powerful greenhouse gas, about 100 times more powerful than carbon dioxide on a per ton basis. But its atmospheric lifetime is much shorter. The decay time is only about 12 years. So we get a prompt reaction in the atmosphere from cutting back on methane emissions. And this model shows a 40% reduction, which is quite feasible with a determined effort. And so you can see that if we want to have a real impact on global climate, we need a combination of both methane to give us short-term impact and carbon dioxide to give us the long-term effect that we need. So I would say that methane is as important as carbon dioxide, certainly over the next 30 years. Now, there's a well-known and time-tested adage that you can't manage what you can't measure. And, but there are easy measurement problems and difficult measurement problems. An example of an easy pollution measurement problem is shown on the left, where two workmen are standing on a big pile of coal, perhaps outside of a coal-burning electric power plant. Now, we know very accurately how much coal we are burning for electric power, how much coal we're burning for industrial processes, and so on. And we also have a very good idea, to within a few percent, of the rate that carbon dioxide is emitting as a result of that combustion in any given process. So you tell me how big that pile of coal is, and I'll be able to tell you, to within a few percent, how much carbon dioxide is being emitted to the atmosphere. Now, a difficult pollution measurement problem is shown on the right. Now, in this case, an aircraft fitted with an infrared sensor was flying over the Permian Basin in New Mexico. The Permian Basin is the nation's most important oil and gas producing region. And by pure accident, it discovered this large plume of methane being emitted from a broken gas gathering pipeline. Now, without that special infrared sensor, this leak could have gone on indefinitely. Methane is an odorless, colorless gas, no odor until an odor is injected in an urban setting. And these kinds of pipelines are not regulated by the Environmental Protection Agency. They're not regulated by the Pipeline and Hazardous Materials Safety Administration. So, and this is representative of a lot of the methane emissions that are coming from our oil and gas industry. We simply don't know how much we're emitting with any level of accuracy or where the emissions are coming from. So this is a difficult pollution measurement problem that is going to be hard to manage. Now, that said, the Environmental Protection Agency does its best to estimate methane emissions from our oil and gas industry. And representative data is shown here. The horizontal axis is years from 1990, when the program started, to 2019, the latest data. The vertical axis is the methane emissions per year normalized by the emissions in 2013. And the data look noisy because the vertical scale is on an expanded scale. So it's actually not as bad as it looks. But what we see very consistently, and one thing about the EPA data, it's not necessarily very accurate for reasons I discussed in connection with the previous slide, but it is pretty precise, and the EPA goes to considerable length to make sure the year-to-year trends are consistent. So if you're looking for a consistent data set over decades, this is where you go. Now, looking at that data, we see that methane has been, the rate of methane emission has been declining steadily but slowly since 1990 at a rate of about 0.3%. Now, this is pretty discouraging because in 2016, the Obama administration pledged to reduce methane emissions from the oil and gas industry at a compound annual decline rate of about 6%. So 6% was promised, we're seeing 0.3%. Now, particularly discouraging is the fact that comprehensive natural gas emission controls were first instituted in 2012. These controls were highly prescriptive, go on for pages and pages of regulation, and somewhat expensive for industry to comply with. And that was sort of implemented in October of 2012. But we see that there's been no change in the rate of decrease of methane emissions before and after the implementation of these regulations. So it seems like these regulations really haven't done anything, and that's pretty discouraging considering all the effort that's gone into them. So why is that? Well, there's a myriad of reasons. I'm just going to show you one example in this short talk, but One type of component that's ubiquitous in oil field operations is called a high bleed pneumatic controller. It's basically a valve which allows you to manage liquid levels in tanks and gas pressures and so on in tanks. So it's an important component. A high bleed pneumatic controller is something that emits natural gas and therefore methane continuously. And in 2012, the EPA said that it was no longer permissible to use this kind of valve in oil field operations. And you can see that industry was pretty prompt in reducing the emissions from these regulated high bleed pneumatic controllers, as shown by the red bars in this plot, where again, horizontal axis is in years and vertical axis is methane emissions from this particular kind of oil field component. So what happened was they stopped using the high bleed controllers shown in the red bars and instead replaced them with what are called intermittent bleed pneumatic controllers. That's the green bars. Now, you can see that although the industry complied with the regulation to get rid of the high bleed controllers, it replaced them with another kind of valve that was apparently just as bad, as shown in the green. So this is very typical of what you see in oil field operations. I'm not saying every oil company is the same, but it's fairly common. I mean, it's certainly universal for oil companies to comply with regulations. They will. They comply with regulations. They will do it at lowest possible cost in both capital expense and operating expense. And if the environmental outcome is not regulated, they don't look at that. And this is a superb example of that. They complied with the regulation. They swapped out a regulated type of equipment with an unregulated piece of equipment, no environmental improvement whatsoever. This is discouraging. And this is one reason why we're not really seeing much improvement in our methane emissions. Now, there is another way to go at this, and that is to actually regulate the amount of methane that's going into the air. Now, in 2012, when those regulations were promulgated, this capability was it was possible, but certainly not widespread. In the intervening years, there's been many surveys which have shown that it's quite feasible and economic to actually go and find methane emitters from oil field operations. And this is a great example. The work was done by the Jet Propulsion Laboratory for the Environmental Defense Fund and just published a few weeks ago. Basically, what the Jet Propulsion Lab did was they surveyed 72,000 sites in the Permian Basin in New Mexico and West Texas. They found 1,100 large methane emitters, ranging even as high as tons per hour of methane. And those are very, very large emitters. Now, each of those emission sources was quantified by plume measurements and identified by owner or operator. So this is really what you need for a sensible emission control regulation. You need to know where your problem is, how big it is, and who's responsible. And we have that data now. From this survey and from similar surveys done by commercial entities in Colorado, in North Dakota, Texas, New Mexico. So there's nothing here that can't easily be implemented. And I've suggested this to the Environmental Protection Agency in the public submission shown in the reference on the bottom of this slide. So with that, I'd like to thank you for your attention. I'm looking forward to any comments that come up in the discussion. And you can reach me directly at my email address, which is shown in red on this slide, and for further discussion. So again, thank you very much. Again, a pleasure to be a speaker at this conference. Good day.